Hello, everybody. It's Loon. Welcome to episode one of Building a Computer. I realize that I may have been a little unclear on what this series was, so let's begin on telling you what it was. The goal of this series was to build a computer and run our own operating system on it. So the point of the series is that individually we will be building every core component of a computer, including the CPU and memory, and then be able to code our own operating system on it. So this episode, we're going to be discussing memory, its functions, and how we can implement it in Minecraft. I hope you guys enjoy the video, and if you guys have anything to say or any questions you have, definitely let me know in the comments. So let's head to learn some theory. So let's try to get into a bit of the theory of memory and what exactly it is. Usually, one bit of memory is arranged like this using four NAND gates. And to simplify this circuit a little, I'm just going to draw it like this. Now it looks a little more simpler, so we can explain what it does. We have the I bit, S bit, and the O bit. The I bit serves as the actual data going to the memory, but it cannot access the memory until the S bit or the set bit is high. And then the O bit represents the actual data. But one bit isn't really useful, so to transition from 1-bit memory to 8-bit memory, all we need to do is add 7 more. But it's a little tedious to control all 8 of these set bits one at a time. You wouldn't want to set one bit individually. You would want to set at least 8 or 16. So we're going to hook up all of the set bits together while keeping the I and O bits the same. Here we have the simplest version of 8-bit memory. We still have our input byte and our memory byte, which were I and O in the previous drawing, but we also have the set bit. This set bit basically protects data from being put into the memory and overwriting what's already there. But how do we keep it from going out? Because we wouldn't want to have every piece of RAM talking to each other at the same time with the data being flying everywhere. So engineers solve this by putting a bunch of AND gates. Basically, we would connect all the inputs of one AND gate to a lever or an input, and then the other input being sent to the output byte of the 8-bit memory. So if you were to enable this, then all the memory that is high would be sent through the AND gates. This is what we call an enabler. We still have our input byte and our output byte, except output byte becomes output of the enabler, and then we have the set and the enable bit. So our set bit basically protects data from going into the memory, and our enabler protects data from going out the memory. So there we go. I'm going to simplify this as this. Now, to fully understand why computers are the way they are and why computer architecture is the way it is, we're going to have to go into a little bit of history on computers. So the very first CPUs had four main registers, the A, B, C, and D registers. These were 8-bit registers. And they stored, obviously, 8 bits. This was the architecture that the Intel 8008 followed. This was the first commercially available 8-bit computer. But when Intel tried to get to 16 bits, they realized that they can't just expand the registers to be 16-bit, because this would fully destroy the compatibility with the 8008. So to solve this, they still realized that they needed 8-bit registers. So what they did is they got their 16-bit registers and just cut them in half. And they referred to them as the higher 8 bits or the lower 8 bits, using the letters H and L. So obviously, AL is the lower 8 bits and H is the higher 8 bits. But remember, they're trying to build a 16-bit CPU, not an 8-bit CPU. So how to solve this, they combined both AH and AL, still keeping their functionality as independent registers, but also being able to control them fully. So AX is basically just AH and AL combined. That's the difference between 8-bit and 16-bit CPUs. But when Intel was making their 8086 chip, they also introduced a couple of special purpose registers, which basically function as pointers, and a couple of segment registers. So let's go to Minecraft and try and implement this. Hello everybody. We're now in Minecraft. So let us take a look at what we have here. This represents 1 bit of memory. Here we have the set, enable, but we also have an extra function in this memory, a clear function. Now, all memory really is this over and over again. This stores one bit of data and makes you able to set it, clear it, or enable it. So let's do a little bit of stacking here. Now we have 4 bits of memory using the same design. Now, it wouldn't really be memory if you couldn't really talk to it or it couldn't save or talk to each other. So let's make something called a RAM bus. A bus is basically something that accesses many other parts of itself and makes everything more connected. So let's add a bus. And there we go. We have one bus. This is 4. This is 1 bit of 4 registers. And so we are able to individually set one of these bits, and it's able to talk to every other bit on this slice. So let's move over here. And this is the full design of both 8-bit and 16-bit RAM. So let's try a little something for this bus. This is the same layout. We still have our enabling functions here, but it's a little different. This represents the lever to enable AL. This represents the lever to enable AH, and this represents the lever to enable AX. So it's a little different compared to most designs, but I enjoy it. So let's try enabling AX. And you'll see a set of repeaters go onto the bus. And if we were to reach the top of the bus, it's currently being displayed in memory. So if I want to write to a certain piece of RAM, say this register, I will first clear it. Notice how all of that turns black. And then I will enable CX, right? And then data gets written to it. So now it doesn't matter what I put into the bus, even if the bus is 0, all zeros, we still maintain our data. You can tell by the oscillating pattern here. Now that we have our 8/16-bit memory down, we need to make our actual 16-bit memory. It's a slightly different design, but it still has basically the core, this memory right here. All we need to do is basically make this 1 rail instead of 2, and make this 1 rail instead of 2. And once we stack that up, we have this. So the only difference between this RAM and that RAM is that you cannot access the lower half the of the register. It's only the full register. And there's enough of these to represent all the registers added later on. And so our full memory design will just be them stacked up on each other. And I have them labeled. So we have our AX, BX, CX, DX, and then all of our pointers. So we have everything we need. And to test that this one works, let's see if there's any memory here. Okay. So this is all ones right here, because all of these are activated, but they're not enabled. So let's enable it and check the bus. Let me get an Elytra, because this might take a while to get up there. And you can see the bus is all ones, meaning that I could write to any register, like this one, for example. Let me clear it first. Clear this register. That is clear. Oh, I was already setting it. Oopsie. Let's clear. And now you see all that is off. All the memory's off. Once I enable, let me set. There you go. It all turns on. Awesome. So this is a